Geometric probability. So our goal is to get, we're going to use that example from before with the Monopoly, or I'm sorry, with the rolling doubles, okay? And you could use it for Monopoly, but I'm just thinking of the rolling doubles. What's the probability that it takes 3 turns to roll doubles? So that means we want to get, we don't want to get doubles on the first turn, we don't want to get doubles on the second turn, but the third turn we want to roll doubles. So on the third turn is where we want to roll doubles, and we use Y for geometric probability. So let's see. This is where we're going to put the probability of what we don't want. So we know it's 1/6 probability to roll doubles. So that must mean that it's a 5/6 probability of not rolling doubles. And we want to do that 2 times. And we want to roll doubles, 1/6 is our probability. We want to do it 1 time. That's the formula for geometric probability. 5/6 times 5/6 is 25/36. 1/6 to the first power is 1/6. I'm going to let my calculator do some math, and it works out to 0.115741. Now, the probability that we did, or the equation that we did, is 1 minus the probability of what we want. So P is the probability of a success, to the power of whatever number we're using, take away 1. Because if you're doing 3 tries of it, you want to get it on the third turn, then technically you want to fail 2 times, or 1 less than 3, and then you want to succeed, this is your probability of success, 1 time. So failing 1 less, and then succeeding 1 time. Unfortunately, this is not given to you on your formula sheet. But I believe there's a way to get this in our calculator. Let's try one more. There's infinite number of possibilities to do more than 3 turns to roll roll doubles. So let's try another example where it is, let's say it takes more than 3 turns to roll doubles. How would we calculate it? Now, a couple ways that we could do this is thinking we want to get the probability of no doubles on the first try, no doubles on the second try, and no doubles on the third try, because 4th and higher would work. Imagine this tree diagram. There's 6 different ways that you roll a die, and then there's 6 different ways that you roll a die, and then off each one of these is 6 more ways where you could roll the second die. And doubles would be like 1, 1, 2, 2, 3, 3. So there is a 1/6 chance of rolling doubles, which means no, not rolling doubles, there's a 5/6 chance. No doubles and no doubles again, and no doubles again, gives you, there's a couple ways to do it, but that's one of them, to give you the probability of rolling no doubles the first time, the second time, or the third time. Probability is actually quite high of that happening. Now, to do this in a calculator, this is not on the formula sheet, but to do this in the calculator, you do the same type of idea where you go to menu, probability, and then 5, which is distributions. And there should be a button for geometric PDF. And you put in the probability and what other question does it ask? The N. So I put in probability is 1/6, and we want to do this 3 times and get it on the 3rd time. Sorry, it doesn't say N, it says X. So I put in 1/6, and you can actually put the division symbol in there. And 3 for your X, and out comes the same answer, which is 0.115741. I think we got up there. Yep. And let's try it with this one down here. If I were to try this, I believe this would be the geometric CDF. So you have to scan down 1 extra, and it asks you for your P, which I'm going to put my probability of getting doubles is 1/6. My lower bound is 1, and my upper bound is 3. And then what this gave me was the probability of getting 1, 2, or 3. And this worked out to 0.421296. And that's the probability of getting a 1, 2, 3. I need 4, 5. I need the numbers bigger than this. So I did 1 minus the probability of that. And did that, I think that's the complement rule from when we were doing our rules. And then I get the same thing as it before, 8, 7. Last but not least, but the mean of a geometric random variable is 1 over P. And this is also your expected value, like we talked about it before. The expected number of trials. We required to get the first success is 1 over P. So some easy questions that I saw. I'll flip the page. Marty decides to keep placing $1 bets on number 15 on consecutive spins of the roulette wheel until she wins. On any spin, there's a 1 in 38 chance of the ball landing in slot 15, where she keeps putting it, or where she keeps betting. And part A says how many spins do you expect it to take until she wins? And the idea of this is if it's a 1 in 38 chance of the ball landing in that slot, then we would kind of expect that it would happen once in 38 chances. So it could be about 38 chances before she would win. We would expect it to take 38 games to win if you win 1 out of 38 times. So that's where that formula is coming from. 1 over P, 1 over, and the probability is 1/38. And when you calculate that, you get just plain old 38.